Hey folks, thanks for taking the time to check out our work on shape from shading for robotic manipulation. I'm Arka, and we are researchers from the Carnegie Mellon University Robotics Institute. Moving illumination can highlight local and global surface properties. On the left, we show the effect of moving a flashlight on the plane of the camera, imaging the curved metal sheet. Moving directional illumination can highlight low spatial frequency surface features, such as curvature, whereas low angle of incidence or grazing illumination can highlight high spatial frequency surface features, such as texture. On the right, we show the effects of overhead illumination versus low angle of incidence illumination on imaging a textured wall. A notable instance of this effect is the gel side sensor, whereby controlling the illumination and fixing the reflectance, researchers could measure the geometry of a surface at a very high resolution. On this slide, we demonstrate a result from our previous work where we designed a sensor to recover the surface depth and normals through contact. Above, we measure a textured metal pin with features of sub 5 mm dimensions by eliminating the viewport of a camera with 6 lights. On the right, we show the surface captured at a sub 5 mm accuracy, colored by the surface normals, also captured by the system. To explore the value and potential of this observation for robotic manipulation, we designed a robot workspace scaled controlled illumination setup for manipulation of Lambertian objects. Our setup consists of 745 watt 5600 Kelvin white LED panels arranged around the robot workspace. We image the workspace with 2 cameras, one mounted on the robot and another mounted to an external tripod. For this initial study, we exclusively look at monochromatic reflectances. Our backend is a photometric stereo system. We capture an ensemble of 7 images corresponding to the 7 lights. We then calculate a per pixel shadow map and use it to invert the Lambertian or L.N shading model as weights. This gives us an initial estimate of the surface normals. But we note that apart from being directly illuminated by the light source, the light from the panels bounce off the walls and ceiling to re-illuminate the different parts of the scene. We capture this effect with a truncated spherical harmonic illumination model for each light and use it to jointly refine our estimates for normals and shadows on the surface. Optionally, we integrate the normals with geometric constraints to get surface depth, as shown here with the colored point cloud. We capture an ensemble of 7 images corresponding to the 7 lights. Looking at the leftmost image, we note that the object occlusion edges are highlighted by the directional illumination. We use this intuition to detect object edges. We visualize the surface depth and normals as shaded point clouds on the right. Our measurements are metrically accurate. Across a variety of objects, we had a maximum surface reconstruction error of 6 mm with a mean error of less than 2 mm. 80% of all pixels across majority samples had a surface normal error of less than 20 degrees, bringing us at par with recent photometric stereo algorithms, far exceeding the common requirements for robotic manipulation. We have overlaid the normals calculated by our system onto the ground truth normals obtained from the mesh. These errors include the warping introduced by 3D printing. We are better than commercial sensors for measuring surface normals. This is because we measure normals by modeling the illumination and reasoning about how the object reflects light back to the camera. This is fundamentally different from commercial depth sensors where the surface normals are obtained as spatial gradients of a depth map. Spatial gradients amplify the noise already present in the data, which is also compounded with the lower resolution of the sensors. The data from commercial sensors were spatiotemporally filtered to remove artifacts. Our normals were calculated from a single instance and has not been processed in any way. Our setup was also useful for identifying arbitrarily oriented flat faces on objects for picking them up with a vacuum gripper. To do this, we first calculated the surface normals and identified the depth edges on the object. We then jointly used these to identify the location and orientation of a face of the object to approach. For the grasp to succeed, the selected face must be smooth enough for the vacuum gripper to seal. We show our results in the form of two movies on the slide. The movies are being played in real time. We could also reliably identify and pick up camouflaged objects. In this slide, we show the results of picking up a 3.25mm disk from a plane surface. Both the object and the background share the same random visual texture. To motivate this experiment, we look at the movie playing right now, where we note a commercial depth sensor, a RealSense L515 in this case, struggles to detect the disk from background even after significant amount of parameter tuning. However, from the images on the top and the movie on the left, we note that the intensity variations due to depth edges are more prominent than the visual textures on the object. We utilize this observation to localize the disk on the plane and pick it up. Like last time, this movie is also being played in real time. Our approach can be used to perceive the deformation of objects by tracking the change of local normals on its surface. We measure deformation in a typical analysis by synthesis fashion. We explain the change in surface normals by calculating the deformation of the object. We present an experiment of capturing the deformation of a PVC card under buckling loads. We visualize the deformation of the card in the top and overlay it on the data captured by the camera. The shape captured by our approach closely matches the theoretical shape derived using beam theory. Please use the accompanying paper for a quantitative analysis and details of the experiment. Our approach was also very effective in estimating poses of known objects, which boils down to image alignment using our system. We are accurate up to 0.5 millimeters and 0.1 degrees in estimating pose. Our multimodal alignment scheme uses object features, silhouettes, surface normals, and occlusion edges, and it is fast and robust to bad initializations or noise in captured data. Interactive results from our pose estimation can be viewed on the paper website. In cases where object models were unavailable, we could estimate the movement of objects through rigid registration. We begin by imaging the object. We then calculate the object surface normals and obtain a point cloud representation of the geometry from the surface normals along with geometric constraints. Finally, we register the point cloud data using general purpose point cloud registration pipelines. We perform experiments on a variety of objects and achieve a localization uncertainty of less than 1.5 degrees and 3 millimeters in plane rotation and translation respectively. Unsurprisingly, dough and clay are Lambertian enough and fit our requirements perfectly. This lets us use our system to measure dough lumps and lumps of clay with precision much exceeding that of a commercial sensor. On this slide, we show the ensemble of images captured using our system, the location of the creases or the depth edges, and the surface normals. The surface normals were optionally integrated to generate dense 3D representation of the surface. Look at the difference between the 3D representation captured using our system on the top right and the surface measured using a commercial sensor on the bottom right. Our data has not been filtered in any way. Through this work, we learned that controlling the illumination of a robot's workspace can yield important information about the surface of the objects in the workspace, especially when the reflectance is known a priori. Obtaining the surface normals by reasoning about the observed shading yields better results than obtaining surface normals as spatial gradients of surface depths. Finally, combining common manipulation tasks of estimating deformation, executing immobilizing grasps, and estimating object poses can benefit from high quality information about surface normals and occlusion edges. Thank you again for taking the time to review our work. More details and interactive demonstrations may be found on the project website.